Hello, very good evening to one and all. Yes, my voice is clear. Can anyone respond in chat box? Okay, let's wait for a few minutes. So remaining people are joining. Yeah, today we are gonna see a introduction about FPGA and the FPGA architecture. So how FPGA architecture it has in what have inside the FPGA. So what is logical elements? So what is a CLB? So we are gonna see in this session. So welcome to one and all. Thank you for joining. So today let's start the session. So what is FPGA? So FPGA we know that FPGA stands for field programmable gate array. So our main advantage of FPGA is we can reconfigure the FPGA. So if you take a processor of CPUs like a microprocessor, microcontroller, or SOCs, so general purpose processors, we can't reprogram those kind of processor, but we can reprogram the FPGA. So what you if you want, we can reprogram as we required. So this is a main advantage of FPGA. So unlike the processor like a ARM processor or any other general purpose processor, it's not like that. So it has a separate architecture, and it has a separate logical element setup, like it has CLBs. So FPGA is fulfilled with matrix of CLBs. So if you see inside the FPGA IC chip, you can find out the matrix of CLBs. So each and every CLBs has consist of lookup tables, multiplexer, flip flops. So it will vary to FPGA to FPGA vendors. So if you take a Xilinx FPGA, so Xilinx means Spartan FPGA, Zinc FPGA boards. That kind of ICs having CLBs. Like it will this architecture based on CLBs, configurable logic blocks. If you take an ultra FPGA like a Max 10 or Cyclone FPGA, Arctics, this kind of FPGAs are based on LAB, logic array gate, array block, like that. So we will see in this session what is a CLB, how it is work FPGA, so how the data transfer inside the FPGA, so how the logic, how many logical elements it has in FPGA. So we are going to see in this session. So basically FPGA consists of CLBs, so configurable logic block. This only you have to take in your mind. So FPGA we can reprogram whatever we want condition. So if you want some if you want do something, you can reprogram in FPGA, not like a processors. If you make one processor, or like if you take any general purpose processor, we can't reprogram that kind of processors, but we can in FPGAs. So you can see here FPGAs can reprogram to desired application or functionality required after manufacturing. So after manufacturing, we can reprogram the FPGAs. So this is a main advantage and a big intro of the FPGA. So let's see why FPGAs. So why FPGA means custom reconfiguration digital circuits. This is a main point. So already I said we can reconfigure the digital circuits, digital designs in our FPGA. So and we can add the peripherals. We can add the inside the by using the FPGA board. We can control the motor, sensors, not more like peripherals. So this is one advantage of FPGA. So we can add the peripherals in FPGA and then modify the CPU. So if you want to in industries, the FPGAs are used to test the CPUs or SoCs. So to run the test cases, they are using the FPGA boards. So continuously they have to pass some stimulus to uh, like a chip. So for that purpose they are using FPGA. So unlike the simulator like a software tool, FPGA giving the real-time simulation stimulus to chip. Based on that test only, they will set like our test case is passed or not. So for testing purpose in industries we are using the FPGA boards. So and then speed for specific computation. So for specific application we can use for FPGA at high speed rate. So these are the reasons why we need FPGAs. So let's move on. History of FPGA. So history of FPGA, it starts from PLA. PLA stands for programmable logic array. Programmable logic array. So it has a consist of OR and AND plane. So there are AND gate, OR gate in a matrix order, like a matrix looks like. But based on that we can program our logic in our PLA. So it is initial stage of the uh, FPGA history. So and then we will move to programmable array logic. So it is also same. It has unplane and R plane, but here unplane followed by R plane. So firstly it has unplane and then it has a R plane. So this is a difference between the PLA. So and then SPLD, it's a simple PLD. PLD stands for programmable logical device. So we can program the device based on it can consist either PLA or PIL. So any of that method it consists in simple SPLD, simple PLD. PLD stands for programmable logic device. So and then CPLD. CPLD stands for complex PLD. Complex PLD means it consists of n number of SPLDs. So SPLD is neither PLA or PIL. In CPLD, it consists of n number of SPLDs. So this form of architecture we can program. It's like a FPGA model, and then the finally we contain we consist the FPGA. So it has n number of logic capacities. So we can write n number of logics inside the FPGA. So we can't write, if you write some logic, accelerator logic in unpain or pen, it is a very huge task to write a logic, and it is very huge task to assign the elements, logical elements, by based on und and R plane. So in the FPGA we have the mux, lookup table, flip flops. So we can achieve all kind of digital circuits. Like if you take any sequential circuits, we can do in FPGA. If you take any combinational circuits, we can do in FPGA. So for sequential circuits, we have flip flops. So by using flip flops, we can achieve the any sequential circuits, digital circuits in FPGA, and also it having the lookup tables. So lookup table means it is like a mux or SRAM like that. So it will lookup table store the previous compute data. So I will show in upcoming slide how lookup table looks like. So these all things FPGA having lookup table, mux and flip flops. These all things comes in under the FPGA. So we can make any digital circuits in the FPGA by using the software tool to implement the FPGA hardware code into FPGA board. So this is the basic architecture, sample architecture for CPLD. So you can see here PAL, like programmable array logic block. So this kind of blocks are connected together is known as a CPLD. So it has a IO pins like IO bank. So this from these blocks we can give input for the PAL, and then it do some arithmetic operations based on our condition written in code. So it will give us output from the IO blocks. So for interconnecting the blocks we are using the interconnection wires. So this is like a bus. It like act like a bus. So we can interconnect the blocks inside the CPL. Yeah, and then we move to this is a main thing you have to aware of the FPGA architecture. So FPGA architecture is fulfilled with the CLBs, and it is surrounded with the IO blocks. So you can see that these blue blocks are IO blocks. So it is used for input output pins. So you can see here all four sides is gonna based on the IO blocks. Why? Because of we are using why? Because of they are using all sides act as a input output pin. Means in FPGA board we can make a PCB in easy way. So if you having the inputs here, outputs here, means it is very hard to make a PCB design in FPGA board. This is on IC. From this IC we have to make a FPGA board. So if you this is a simple and easy way to make if you follow this architecture, we can easily make a PCB, FPGA PCB. So then only for that only they are using this architecture. So all sides are having pins. So each side it's like a bank. This side is a one bank, first bank, like this is a one first bank, the second bank, third bank, fourth bank. So these are the banks also we can identify the pins in FPGA. So the main thing is for making PCB easy, and we can make a circuit easy. For that we are using the all sides as a IO banks, IO pins. So and then inside the box you can see here it is a logical blocks. It means configurable logic block. So this is the logic block. Inside the logic block it having some architecture, some designs I will show in upcoming slides. So it do something. If you write in some half adder code for full adder code, they will come here. So in this logic block only they will assigning the uh, gates like latches or lookup table. They do some arithmetic calculation based on our RTL code, and then they give us output from this block. Based on our condition, based on our code, it will act it will use the CLBs. If you are writing the very simple half order code, it will use only one CLB. If you're using complex code like a big code like a FIFO memory, FSM, or any other UART protocol, if you make, means they will use more CLBs for the for our project, for our design. So they are giving output, and then for connecting the CLBs. So for connecting CLBs and IO input output blocks, we are using the programmable interconnect wires. These lines are act as a wire. So these wires on this based on this wire only we interconnect the CLBs and these input output blocks. So the wire is very important thing in architecture. So this wire only it will connect the whole FPGA interconnectedly. So if it why? Because of if imagine if you have a large design code, so it will take to half of the CLBs in FPGA, but the output pins are very low. So it must have to interconnect all the CLBs, and then it will pass the output as say only in one single wire. So we have to interconnect these all wires for get output in one wire. So for that we have we are using the programmable interconnect. So this is the architecture of FPGA. So this is the CLB. So whatever you see in the architecture, this block, inside the block it has something like this. So it having the lookup table, flip-flops, and the mux. So basically lookup table is used to do a combination logics. So combination logic means it adding adders, full adder, half adder, and then multiplex. They are comes under the combination circuits. It doing the combination logics, and then flip-flops are used to do the sequential logics like counter, register, like that. So these are the usage of the flip-flops. It will do the combination logic, and then it will do the sequential logic flip-flops. So in the each CLB we can only pass the 4 inputs only. So for in each CLB we can use only 4 inputs. If you in your design code or RTL code, if you are using the more than 4 input means, it will take additional CLBs by neither like a neighbor CLBs. So this is the CLB architecture. So based on our condition in the code, it will do some operation and then it will give some output. This output will connect with wire, and then we can get output in the output pins, IO pins. So this is FPGA architecture. So it has, firstly we have to take into mind is it is matrix in order. So inside the FPGA we have the matrix of CLBs. So inside the CLB we have the uh, structure like it have consist of lookup table, flip flop, and then mux. So this all comes together, it has called as CLBs. So lookup table is used to store the pre computed value. So if you take an it act as a SRAM, so single bit SRAM. So if it has 4 input means it has 4-bit SRAM. So whatever it has pre-computed, that values are stored in the lookup table. If you're doing the full adder operation, it will store the some operation, some output here after the completion of the full adder. Then and then another CLB, it will another in the another CLB it store the carry output here lookup table. So another CLB has a lookup table. So on that LA lookup table it will store the carry output. So in the if you're taking the fuller operation, it will take 2 CLBs. In the first CLB at the lookup table it store the some output. In the second CLB at the lookup table it will store the carry output. So this is the main of the CLBs. So and then the another advantage is we can assign the CLBs as whatever you want. So if you want to assign a DSP block some CLBs, we can assign like this. So if you return a DSP logic in your code, it will automatically assign this some CLBs for DSP, but for DSP. And then if you make a one FPGA in the fabrication stage, you want to assign some CLBs, some elements as a DSP block, we can do in the FPGA fabrication. And then and also like a RAM. So we can see here this box are act as a RAM. So we can also assign as a RAM. So, so this is a one feature advantage. So we can assign the whatever you want DSP block. If you want, you can assign the DSP block in the FPGA, and then you can if you want to make a RAM, so you can also make a RAM in the FPGA architecture. And then so you can, this is example for the SOC come FPGA. So SOC means we know that it having the CPU inside a single chip. It has all the components like a CPU, processor, memory, and then DSP block or IO pins or peripherals. So these all things are comes under in a single chip. It's called SOC. So same like in FPGA, we can also make a SOC kind of thing. So you can see here this is example architecture for SOC. It is inspired by Zinc FPGA. So Zinc FPGA architecture looks like this only. So it has ARM processor and then PCIe Express. So PCI is used for communicating the hardware and like a hardware means memory block to CPU. So for example, if you take your computer, you having the GPU and the CPU. So to communicating the GPU and the CPU, industry people are we are using the CPI protocol. So there is one protocol, it's called a peripheral component interface. So we are using the PCI protocol to communicate the GPU and the CPU in our systems, Windows or computers. So as well as if we can make a PCI in our FPGA. So and then this is the basic architecture for SoC cum FPGA. So it has a memory block, IO blocks, CLBs, some RAM memory blocks, some DSP blocks, some PCI Express. We can use also ARM processor inside the FPGA. That is an example. If you ask some example means Zinc 7000 FPGA boards. It comes under the SoC come FPGA board. It has a ARM processor inside the FPGA. So this is architecture for that. This is sample architecture for that I'm saying whatever I'm saying. It is a sample architecture for that. So okay. So and then we'll move to the internship. So So if you guys are really interested, you can convert this masterclass into 21 days masterclass into 1 month internship of on FPGA. So you will get the benefits of all 30 days recording session, all 30 days presentation PPTs, and exclusive codes you can download also, and then VIP community group for your doubt clearing and the internship updates. So and you will get the internship certificate confirmation letter from IETE, and then you will get a 90 days LMS course access. In the LMX we having the LMX it having the 30 days recording sessions, so you will get the 90 days access for that, and then you will get the assignments and tasks, and we having the weekly live sessions for your doubt clearing, and then we are giving also building resume building mock test and internship, and you will get the participation certificate end of the internship. So these are the benefits you are getting at this fee of just 999. So our regular fee is 399. It is our regular fee. In this masterclass sessions we are providing our internship at a discounted fee of 999. So if you guys are really interested, you will get by using the this registration link, and also you will get the link in chat box to for registration. So this is a limited time period offer. So this offer will close at 16th March. So let's move to Maxton architecture. So yesterday we seen a Maxton FPGA FLK board, that green color board. It having this architecture. So if you see inside the FPGA, it will look like this only. So it has PLL, phase locked loop, and then internal flash memory. Like yesterday we said, like UFM, CFM, user flash memory, configurable flash memory. So these two memories are inside the FPGA. So these are the logical blocks in the Maxton FPGA. So yeah, you can see here there is one red line. So this red line is called the clock line. So we have the clock oscillator out of the FPGA, outside of the FPGA. So the clock oscillator will give the clock input for FPGA IC. So imagine this is one FPGA IC like architecture. So every system uh, uh, every system will work based on clock. So one general question, if someone asks to you, so which part will start first while you switch on in the computer? So if you switch on in the computer, which part will start first? So basically the first part is switch on means that is very important, is a clock oscillator only. It must be switched on the firstly. Why? Because of all the instruction, all the data transferring based on clock. If you take in any computer laptops, the clock oscillator is very much important. Based on the clock only we are using the computers. Why? Because of every clock pulses only there are some conditions based around the clock pulses, passage or neckage of clock. So we will see in the upcoming sessions. So the main thing is, if you use in the computer, there is a very much need the clock must be on. So clock oscillator will give the output. If the clock oscillator will fail to give the output means we can't use the computers. So this is a main important of clock. So we can say like a memory is important, or processor, or any controller is very it is important, but for that controller memory the clock is important. So based on the clock only it will work. Any chip, if you take any chip, based on the clock oscillator only, it will perform the instructions. So if you boot some, if you while booting your computer, you can see some random instruction comes over in black screen, like a boot up stage. It will initiate by the clock. So this is the main about the clock. So for FPGA also we need a clock. So the inside the, so we assigning the one separate array, like a one separate block as if for a clock. And then this is the this blocks is called as a lookup, LAB, logic array block. So Xilinx FPGA having the CLBs, configurable logic block. But in Altera FPGAs, so if you take an Intel Altera FPGAs, it consists of a logic array block. So logic array block and configurable CLBs, like a logic array block, we call it as LAB. LAB and CLB both are same only. Both are having the inside the lookup table flip flops mux. But in logical array block there is added feature. So I will show in upcoming slide. So this is architecture or in Maxgen FPGA board, in our FPGA board. So it has you can see here all four sides it having the IO banks for the input output communication outside of the board. And then it has the ADC block. So we can't direct, if you having the two pins, one is digital pin, another one is the analog pin. So in the digital pin we can't transmit the analog signals. So this is the main thing. So in the digital pin we can't transmit analog signals. For that we are using the separate analog separate block. So in that block it having some pins. In this, by using that pin only we can transfer the analog signal, we can compute some calculation by the analogs from the analog signals. So this is useful for analog digital transmissions. If you are getting some analog input by using this one, by using this pin only we can get the analog inputs. So we can't use general purpose IO pins. So in this IO bank, like a general purpose IO pins, we can't transmit the analog signals. In this pin only we can transmit. So every FPGA board consists of analog pins. It is at limited pins, but by using that pin only we can process the analog signals. And then it having the internal flash. So it has two flash memories, UFM and CFM. So UFM stands for user flash memory, CFM stands for configurable flash memory. So both are storing inside the chip, so inside the FPGA. So this is the main thing of our Maxgen FPGA board. So it has the these kind of things like a PLL. So PLL means that this PLL, like you can see here, four PLLs. PLL means stands for phase locked loop. So by using the PLL, we can increase the clock frequency or we can also decrease the clock frequency. So imagine in your design code, you are using the high frequency. So our clock oscillator will give the 50 megahertz, and then for some condition you will need the 100 megahertz clock for some task. For that we can use this PLL to make the 50 megahertz clock to 100 megahertz. And then in some other condition we have to use for 25 megahertz. So we have to reduce the 50 megahertz to 25 megahertz clock. For that we are using this PLL. We can use this PLL. So based on changing the frequency we can use PLL. But all PLLs depends on clock oscillator, our global clock oscillator. So this is main thing. So if you increase in the clock, if you increase in the clock frequency, that clock based on the original clock, like a global clock oscillator. So we can use PLL for clock increasing the frequency, and also we can do in counters. By using the counter we can increase the clock frequency. So but for that, if using counter means you have to write the counter code counter code to get that certain clock output, like a clock frequency output. So this is architecture for Maxgen FPGA. So it has a UFM CFM on chip memory, and then it has IO banks around the four sides, and then it having the PLLs, four PLLs, and now it have the separate analog to digital pins. Here let's move to so this is how clock You can see here I said no this clock pin, this clock array, how it works. So it will works like this only. So it will pass the clock all parts of the FPGA. So if you divide the FPGA means in we can divide in four banks of FPGA. This is the first bank, second bank, third bank, as you want. If you divide means we can divide like this. So we have to pass the each bank clock inputs. So for that we are passing here like a clock 0 and 1 here, clock 2 and 3 here, and then clock 4 and 5 here, and then clock 5 and 6 here. This is the using of clock inside our FPGA. So and then we'll move to PLS. So I already said no how PLS is working inside our FPGA. So we having the PLL 1, 2, 3, 4 like that. 1, 2, 3, 4. So we having the 4 PLL in our national FPGA. Some FPGA boards for some FPGA IC chip don't have that much PLL. On that time on that certain time we may have to use the counters to make a required frequency. So and then let's see the FPGA design. So FPGA design is based on making, first we have to write the RTL code. By using the tool we can flash into FPGA board. So it is comes under the software program is implemented in hardware. So you can see here we are using software and also we are using hardware to make a FPGA design. So this is the usage of FPGA. So unlike the processor, FPGA process like dedicated hardware don't have any operating system. So this is the main thing in FPGAs. We don't need any operating system to run the code, to execute the code or to simulate our code. So we don't need any OS operating system to do some operations. But if you need it is only need for if doing high-end projects like we can do AI projects like machine learning, deep learning. We can do in Xilinx Zinc board. For that high-end projects, high-end usage of the feature, we must use the we have to use OS. So there is a ping board in market. The ping board there is a ping OS in also market. So in FPGA board we have to insert our SD card to to the OS, and then based on our feature zinc ping board peripherals we can use for edge detection, object detection, image processing like that. So we can use the OS in FPGA in the separate FPGA boards like pink FPGA, zinc FPGAs. So why? Because of zinc and pink FPGAs having the SoC kind of thing inside the FPGA, so we can use for the high-end usages like image processing, AI projects, machine learning kind of things. So basically, FPGA vendors are Intel Altera, Xilinx giving the Spartan boards or Zinc boards. Then Lattice also, that Lattice is one kind of company. They are also providing the FPGA boards. So these companies are vendors for the FPGA boards. So this is a FPGA design flow chart like a hierarchy. So first we have to design entry, and then RTL design and simulation, synthesis, implementation, testing and debunking FPGA designs. This these are the stages in the FPGA design flow. So let's see one by one. So firstly design entry. So design entry means we are writing the RTL code in tool. So if you take an Ultra FPGA, for Ultra FPGA, we have to write a code in Intel Cortex Prime. So we are using the tomorrow we will see the how to install the Intel Cortex Prime. It is one tool for the Ultra FPGAs. So in the FPGA, we are writing the RTL code in Verilog or system Verilog. It will convert into the schematics. So schematic means logical circuit like a digital circuits by using the AND gate OR gate. So that by converting the RTL to digital RTL to schematics, this process is take care by the tool. So we don't worry about that. And then there is another way to make a design entry. So we can convert the schematic to RTL. So that's a two thing. So we can convert RTL to schematic, and then we can do like a schematic to RTL. So we can do both in tools like a Xilinx, Vivado, Intel Cortex Prime. So in the master class we are gonna use only RTL to schematics. So in this master class we are gonna use Verilog code from the outer from the Verilog code, and we convert into the schematics in the tool as the Intel Cortex Prime. So we are using the Verilog tool in the master class. So we'll see in the upcoming sessions. So this is a design entry. Converting the RTL code into the schematic is a design entry. So this is our design code. So there is a one keyword, technical word in VLSI semiconductor industry. If you're writing the design code, if you're writing the RTL code, top level code is called design code. If you're writing the test bench like in system Verilog UVM, it's called test bench code, verification code. So design code means RTL code, verification code means it having some system Verilog UVM coding. So and then RTL design and simulation. So we have to test our design code by using the simulation in our tools. So every tool having a simulation kind of thing. So we can use the simulation option to verify our design code. So we can't directly flash our design code into FPGA. If I do means I can make mistake in our FPGA. So or else I can so without simulation, we can't verify the design code. Based on our simulation only, we can ensure that our code is working correctly. We can implement into a feature, so we can come into that result by using the simulation. So that like tools can give these kind of options, simulation options. So we can simulate our design code, then we can verify the design, so we can implement it. After that, we have to implement in a feature. So and then this is another stage like a synthesis. So synthesis is nothing but converting the RTL code into logical gates. So this is example for that. This is simple AND gate, and this is the example for the synthesis. So the tool converting the RTL code into synthesis logical gates, logic gates. So our, our input is transformed into netlist that is called logic components, and then it will also assigning the wire. So taken full adder, full adder consists of AND gate and XOR gates. So for connecting the one gate to another gate, we must need one wire. So the tool also assigning the wire. So wire means nothing but netlist. So this kind of thing. So I will tell you upcoming slide session. So for this assigning the logical blocks, logical gates, and then logic wires, it will take care by synthesis. But our code must be correct in synthesizable. So if our code is not synthesizable, the tool will not make a design. It will throw an error. Why? Because of our code must be synthesizable. So there is a lot of rules in while writing the code to our code look like synthesizable. So we have to follow that rule, then only we can write the code like we can write a code like a synthesizable code. So and then we'll move to implementation. So in the implementation part, there are three main things like a map, place, and a route. So mapping means convert the logical region into a feature resource. So mapping means it will assign the CLBs. If you're writing some logic in your FE code, it will assign the CLB. So that tool, like that tool assigning the CLBs, and then place assign the mapped elements to specify the FPGA locations. So it means if you choose if the tool choosing some CLB in FPGA, and then they are assigning the signals to particular CLB. So each and every CLB consists of lookup table, mux, demux, uh, uh, latches, we seen before. So that kind of things we have to assign some input output signal in our FPGA. So that kind of things, assigning things comes under the place. So mapping and placing will take care by the this all three process like mapping, placing, routing. These all things done by the tool only. So we have to write only code and we have to simulate the design code. Mapping, placing, and routing. This all take care by the tool. It will automatically assign the CLB and assigning the pins, assign the process the condition, so it will give output and it will assign the output pins. So just we just assign the assigning the output and input pins. It will take the it will take care of the CLBs, latches, lookup table like that. So and then route. Route means connect the placed elements using FPGA interconnect. So routing means I already said no. For interconnecting the CLB, we are using the programmable interconnect wires. So routing means that is only. So for assigning the wires, it is also one process. Based on the wire only, by using the wire only, we can get the output from FPGA. So wiring assigning wire is very important. That is comes under the route operation. Mapping means choosing the how many CLBs you want are need in design code. They are choosing by the map. They are FPGA declaring CLBs, and then placements. It will assigning the input output signals on CLB. Route means it will assign the wires for to get the output. So for getting output, wires are used. For assigning the input output signals on CLBs, the placement place is a process, and then a mapping process is use assigning the CLBs for our based on our design code. So this is the main thing of the implementation. These all things are taken over by the FPGA software tool. Like if using Intel Ultra, Intel Cortex Prime, that will take care of these all three kind of things. So and then testing and debugging. So for testing and debugging, we are using the simulation in our tool. So this is one process. So this is the I already said internal clock internal structure of FPGA logic block routing IO. So we know that these are the internal structure of an FPGA. So logical blocks. So I already said no CLBs. Configure logical block consists of a transistor pairs, combinational gates like a basic NAND gates or XOR gates or an input lookup table. But in our machine FPGA we having the 4-bit input only. So we can in current market rate we are using only 6 input lookup table only. 4-bit and 6-bit input lookup for lookup table. So and then lookup it consists of multiplexer and then wide fan. So these are the components inside the CLBs are like a logic blocks. So and then advantage of the FPGA design, do anything circuit. So you can do any digital circuits in FPGA, super fast, field programmable, so massively parallel, so high input output pins. So we know that our yesterday I said no Intel Master, that green color board, it has 484 IO pins. So it has 484 input output pins. We can using as we want. So high input output pins. So these are the disadvantages of the FPGAs. So maybe expensive. So some FPGA board we can get by less amount, like a minimum amount. But if using the high end FPGAs, it will cost up to 20,000, 30,000. So there is a expensive one. It's a disadvantage, and then high power. It consume the 5 volt as input. So it is also one of the disadvantage. And then volatile and boot time, it take boot time. So I pin count also one complicated thing for assigning the input output signals. And then many traps is there, like if you assign, there is a tool, sometimes tool get confused how to compute the CLBs, how to assign the CLBs. So for that we have to design we have to write our code correctly. Then only we can say we are trap free. So and then tool also complex. So if you're using Xilinx, very simple thing. Vivado is little more difficult than Xilinx. Intel Core Prem, it is little more difficult than Vivado also. So both Vivado and Altera, sorry, Intel Core Prem, same like thing. But if you can't learn usage of a tool in one day, so it will take up to 2 days how to use that tool. It having lot of options, it having lot of design options, timing analysis, and the clock PLLs and then simulations. So it will take more time to learn the tool usage. And then these are the disadvantages in the FPGAs. So these are the things of application of FPGAs, like we can use in aerospace, medical, digital signal processing, video and image processing, automotive data centers. But we are mostly using in medical and aerospace. So in aerospace, we can't use commercial or private FPGA, private microcontroller boards. For that reason, the aerospace engineers will make a separate FPGA boards for the aerospace scenarios. We can't buy directly, so we can't use for the common man. We can't use that kind of FPGAs. So in medical scenarios, we are using FPGAs like if you take any ECG or any kind of signal, ECG machine, or any light sensing like a laser operation. So this I don't know clearly, but most of medical gadgets or medical equipments, it must contain, it may be contain FPGA boards. FPGA, not like FPGA board, like FPGA ICs, FPGA chips. So digital signal processing, we also using the FPGA board. Video processing we can use, automated system we can use, data center also we can use. So these are the applications of the FPGAs. So coming to conclusion, you have to take into mind means every FPGA board consists of matrix of CLBs or LAB, logical array block. So Xilinx consists of CLB. Altera FPGA consists of LAB, logical array block. Each and every CLB consists of lookup table, mux, flip-flops. Based on these three things, we can using the we can do the arithmetic operation in the FPGA. So this is the thing you have to take in your mind. And the lookup table for the combination logical, and the flip-flops for the sequential logical. If you want to do combination logic, that logics are processed worked in lookup table. And then if you're using the sequential logic, this sequential logic take care by the flip-flops inside the our CLB. So this is the thing you have to aware of the feature architecture. So thank you guys, thank you for listening. Tomorrow we will see the how to install the Intel Cortex Prime Lite Edition tool, and how to get access from the Intel company. So for if you want to download the Intel Cortex Prime, you have to register the Intel declaration, like kind of thing. You have to register with your mail ID password. Then only they will give the tool for you at free. So Intel Cortex Prime Lite Edition only free, open source. So we can use that. So that tool installation we will see tomorrow. Thank you guys, thank you for listening. We'll see tomorrow.